Hello and welcome everyone to the next session of Introduction to Biomedical Optics from Theory to Applications. Today we talk about one of the applications, that is Raman spectroscopy. In the last class we talked about fluorescence spectroscopy, fluorescence imaging. Today we talk about Raman spectroscopy. So we discussed about different modalities of imaging, and in the end of the day we are imaging not a monoatomic species or diatomic species, but a polyatomic species such as hemoglobin. So it's kind of very challenging to decipher what composition do we have in the blood, for example. Okay, so we talk about different light matter interactions. One is the absorption. Okay, here once you shine the light, you get the light being absorbed within the vibrational levels of the ground electronic state band, and this vibration actually is this energy that it absorbs. It ends up into different vibrational modes such as stretching, scissoring, and wacking. There are 6 more modes of how the molecules actually vibrate. Then we talk about 2 different kinds of scattering, that is elastic scattering, where there is no loss of energy, and inelastic scattering, where there is some loss of energy. In the case of elastic scattering, we talk about 2 types of scattering. One is Rayleigh scattering, other is Mie scattering. Rayleigh scattering is why we see the sky as blue in color, and Mie scattering is why we see the clouds are white in color. We already discussed this in the earlier sections. And then we have talk about inelastic scattering, where we shine the light and there is some change in the energy once the light interacts and then comes out from the of the sample. Okay, in elastic scattering we talk about fluorescence, that is we shine the green light and we get the red light, and the next thing that we discuss is on the Raman spectroscopy. Okay, so today we are going to focus on Raman scattering, Raman spectroscopy, to understand what is going to happen. Okay, in reality, as I already said, in the case of tissue, which is kind of very complex arrangement of different compositions, we have a lot of tissue constituents. We will try to simplify the things and then try to see more complicated structures. The first thing, before you go ahead and try to learn a Raman spectroscopy, we need to first learn spectrometer. What is a spectrometer? So what is a spectrometer? We shine a light source. It would be a monochromatic light source or a compound light source like white light, and we use a mirror to bend the light to a grating. Now this grating is a very interesting structure. It's a dispersive media. I mean, it actually disperses the compound light source into, it bends the light source, different components of light source into different angles. Here you can see that if it is white light, it's going to bend green to be little bit lesser as compared to the red light. So, once you have another concave mirror, you can actually bend each component of light source in a different angle, and you can detect it using a detector. It could be a linear detector which you can use to detect this compound light source. Okay, so here you can see the light was actually in a single beam, but here you can see the angle with which the light is approaching is actually different. So each pixel or each detector element is now going to detect with respect to a specific wavelength. Okay. Raman spectroscopy was discovered by Raman with one of the structure that you see on the right hand side is showing is that of the benzene. You can see a particular area which is white, and that actually was the start of the Raman spectroscopy, one that you can see over here. So this is the Rayleigh scattered light, and this is the Raman scattered light that you can actually see in this film over here. So what do you need for Raman spectroscopy instrument? You need a light source. You need a sample. It could be in a cuvette, for example, or you can do it on your skin as well. At a later stage we will see about how you can do it on your skin as well. You have a dispersive element. The grating is one of the dispersive element, and of course you need one filter and then a detector. Okay, a filter is required to remove the Rayleigh scattering out, and you actually focus only on the Raman spectra. Okay. Before we go into we dive deeper into Raman spectroscopy, we need to understand few of the terminologies which are used in Raman spectroscopy. You have already been known about energy, frequency, wavelength. Something new that you will hear is the wave number. Okay, a wave number given by nu, nu, and that nu is defined as 1 over the wavelength. Okay. So, in most of the cases in Raman spectra, when you see the Raman spectra, you will see not the wavelength, not the frequency in x-axis, but you will see the wave number. So, it is another way of representing the wavelength variation. And then you have the light intensity, of course, that is how much of the light is being shine on a particular surface. Okay, so we talked about absorption, means if you have a compound light source, you have 3 components, you have red, green, and orange in this case, just a representation of the compound light source, and you will see that after the interaction with the cuvette, the red component of light is being absorbed, green is little bit less absorbed, orange is actually passing through. So, this is an absorption of a specific wavelengths. Then we talk about fluorescence, that is I shine the green light and what I get is something like a red light out of it. Okay, so fluorescence phenomena that we are actually able to absorb. And then we have a Raman, that is we shine a red light and what I get is not just the red light, but we also get a lot of different components of the red light. I want to show you, for example, what I have is a laser pointer. Okay. Now what if I say to you is that this laser pointer, so I think you are able to see my screen, my hand, and I am shining this red light to my hand, and I think you may be able to see this red laser pointer which you are able to see. Now what I am saying is that the red light that I am shining on this surface is not what you are actually able to see. So, it is not just the red light that you are able to see, but there is extra something else also that you are able to see. Now for example, I shine now the same laser pointer not to my skin, but now on the nail. Okay, I am shining the red laser light to my nails. Okay, what I am saying is that eventually is that the light that you are seeing from the nail is different as compared to the light that you are seeing on the skin. Okay, this may not be true by visualizing through a naked eye, but if you have a more sophisticated optical instrument detectors, then you would be able to appreciate that, yeah, definitely the light that you see from coming out of the nail is different as compared to the light that is coming out from the tissue, and that is what we are going to study. So for example, here you can see I was shining the light of 630 nanometers, 640 nanometers perhaps. What I am going to show you is a laser light at around 530 nanometers. So I am shining a light of 530 nanometers, and what if I say is that what you are observing is not just the 530 nanometers, but there are some extra components of light also coming in. Okay, that is the signatures of the light. So you will observe Stokes Raman scattered light, which is having a higher wavelength, and anti-Stokes Raman scattering would be at lower wavelength. Okay, so here you can see on the top x-axis is the wavelength, and on the bottom x-axis is the wave number. Okay, so you can see this, and you can actually comment on what you can infer is that the Stokes Raman scattering is having a higher intensity, which actually makes sense as well because it is higher wavelength, right. So having an energy from a particular energy to a lower energy that is higher wavelength makes more sense as compared to higher the energy, lower the wavelength, that is even more difficult. Okay. So what I am saying is that when you see this light over here, it is not just the red light or this 530 nanometers light source, but there is also an extra component that you are able to observe, which you might not be able to see with naked eye, but with a sophisticated detector you would be able to see. Okay, so this is where I am actually shining my light in the spectrum, and this is the extra thing that I am seeing on the left hand side and on the right hand side, and these signatures would be different for each of the components in the whole world. Okay, this signature would be different from the nail as compared to the skin. Okay, both signatures would be different. Okay, and in the next class, rest of the class, what we will be discussing is going to be the Stokes Raman shifted scattering spectra. This is what we are going to cover in the next class, or whatever in the rest of the class. Okay. So you can see that the light that you are actually original light source is the Rayleigh scattered light source that you are able to actually see, that is the elastic scattered light source, and then there are inelastic scattered light source, that is Stokes as well as Anti-Stokes. The Stokes are also called as Raman scattered light source, and here this is the significant amount of significant events that are going to take place is more in the case of Raman scattered light source as compared to the Anti-Stokes, specifically because you can actually impart the energy based on the molecular vibration to the light source. But in the case of Anti-Stokes, what it is saying is that I am shining 530 nanometers, but I am actually getting around 520 nanometers. Lower the wavelength, higher the energy. It is very difficult to get out something which is having a higher energy as compared to the energy that I am imparting to the surface, right. That when it is possible, when the molecules on my skin actually is already vibrating, few of the molecules would be vibrating because of the thermal energy that is surrounding us, they would be rotating with its own energy, and that energy is being transferred to the output light source, okay, in form of energy reducing the wavelength. Okay. But it is extremely rare event that you see an Anti-Stokes, but the Stokes, that is the Raman spectra, is what you see it often. The probability of the number of events taking place for Raman shifted photons would be more as compared to the Anti-Stokes photons. Okay. But it is still rare, so you need to have sophisticated detectors as well as filters to remove the original light source, that is a Rayleigh light source, and then detect only the Stokes light source. We will see how do we do it. Here you can see I am shining a light which is around 488 nanometers light source to the cuvette, and you can see that it is actually able to right now there are two images over here actually, one which is on the left hand side, another is on the right hand side. I am seeing this cuvette without any filter, and here I can see the blue light coming out of it because I am shining a light which is at 488. This liquid inside this cuvette is a cyclohexane, it is kind of a benzene component inside it. Now on the right hand side is the same cuvette with the same cyclohexane liquid inside it, but now I am observing with a filter. Okay. This filter has a very unique characteristic that it will remove the blue light. It will only allow, it is a long pass filter which will remove the blue light with which I am shining to this cuvette, and it is only going to give you the output which is just more than the blue light, okay, little bit more than the blue light. So there is a long pass filter which removes the original light source, and only the higher wavelengths of the energy we can actually observe. So here you can see now is a Raman spectra of a liquid which is known as benzonitrile. It is a colorless liquid, but that also has a specific Raman spectra. Now each peak of the Raman spectra signifies some bond or a particular composition. So for here example, this peak at around 2210 signifies a bond between, triple bond between carbon and nitrogen. Okay. Similarly, the peaks at around 900 and 1200 signifies a benzene bond with carbon and triple bond with nitrogen. Okay. So each of these peaks in the Raman spectra signifies a particular bond or a particular chemical component. Okay. And it would be different for each and every material that you have. What you see in over here, you can see my laptop screen, it would be having a different signature as compared to my skin. Okay. So here is the common example of aspirin and paracetamol. People use Raman spectroscopy to understand whether it is really aspirin or not, or it's a fake medicine. Okay. In pharmaceutical industry, a lot of Raman spectroscopy have been already been used. So here you can see those peaks that are coming up, they are specific with the presence of aspirin, and these peaks are specific with the presence of paracetamol, right? So they both are having very close to each other. Okay. Now, for example, you want to know whether the pearl, whether it is actually original or not, right? So whether it is a fake pearl or not. So you can, how do you know that? You can actually do it. You can do actually a Raman spectroscopy on that pearl. Here you can see for calcium carbonate there is a specific peak at around 1050 centimeter inverse, that is now shifted into wave numbers. Okay, now x-axis is wave numbers, no more it's wavelength now. Okay, and the pearl that you have done is also around the same value, 1050 nanometers, sorry, 1050 centimeter inverse. But in the case of a fake pearl, you can see that the signature are not being generated for the same thing. Okay, so at the same specific location, it's not there. Right? That means that it is a fake pearl. It's not the original pearl. Similarly, you can actually see there is a cat on the left hand side, an ivory cat, which is made up of ivory. Okay, and there are many necklaces which are made up of ivory. You want to know whether it is an actual ivory or not. So you try to see a specific peaks at specific locations. For example, over here at 60-50 centimeter inverse, you can see this for original ivory there would be a certain peaks, but in for which are fake ivory there are no peaks over here. Similar to this, you can actually also see historical maps people use, whether it is original or not. You can actually see from its Raman spectra. Okay, so whether a map, you can, it's a very old map, you want to see certain pigments, whether it is actual original very old pigments that are used, or someone has made a fake historical map, you can actually do this testing as well. Now the most interesting part of Raman spectroscopy is that it is not hindered to any specific laser light source, or it could be maybe I need to always use green light, or it needs to be blue light, or it needs to be infrared light source. For here example, you have a polystyrene pipe that you see over here, and I try to shine this polystyrene light pipe with three different wavelengths. When I shine with 532 nanometers, that is green light, I get this particular Raman spectra. Okay, when I shine with a red light, that is 638 nanometers, I get this Raman spectra. Okay, so here understanding that I have removed the Rayleigh scattered light source. Okay, here the Rayleigh scattered light has been removed, and then I shine with 785 nanometers, then I get this particular spectra. Okay, now what is the difference? Right, so in each of the cases we actually get the Raman spectra. Now we can actually put those values instead of the wavelength, we can put in terms of wave numbers, and you can compare each of them, and you will see that when we put that in terms of wave number centimeter inverse, the peak will actually correlate. Okay, the peak will actually come at exactly the same time. So the next question that comes to your mind, which wavelength should we use for a certain application, right? For example, if you're doing a biological applications, then you will go ahead use the infrared light source instead of using a laser of visible light source. Because why? Because in the case when you use the visible light source, you will get fluorescence. Okay, in the case of infrared light source, when you shine on the tissue, you will get a very minimal autofluorescence. Okay, this will help you to differentiate your Raman spectra as compared to the autofluorescence. Okay, when you are actually doing the study, you always do it in a kind of a cuvette. Now the question that comes is that the walls of the cuvette also interact with the laser light source in addition to the material that you have, analyte that you have inside the cuvette. Now each of this material, they have their own, they are made up of silica, right, so, or a quartz. So they are made up of a certain component, and those the signatures, the Raman spectra of those signatures also need to be removed when you do it for a specific analyte. So when you get a cuvette and you put the sample and then you do the Raman spectra, that Raman spectra would be of the analyte and the quartz, or the whatever the cuvette material is made up of. If it's a PTFE or it's any plastic material, those Raman spectra would be overlapped with the Raman spectra of the analyte. So it's very important that you remove that manually remove the, so you do the experiment only with the cuvette and you see what is the Raman spectra, then you remove that Raman spectra from the analyte Raman spectra. Okay. So as I said, different wavelengths are used for different analyte. So if you have if you are looking for inorganic samples trying to get a strong signals from them, then you use 405 or 532 nanometers. If you are looking for balanced signals with fluorescence in organics, then you use 633 to 830 nanometers. And then if you are looking for specifically biological samples, right, where you want to reduce the fluorescence as much as possible, then you actually go ahead with 1064 nanometers. There are a few examples you can see in the case of cyclohexane, acetaminophen and coconut oil. We have tried with 3 different, not me, the work that was given over here, they have tried with 3 different wavelengths, and you can try to see that for example over here the red, this 785 nanometers is the best to see the Raman spectra. Here the 532 nanometers is good to see the Raman shift at 3000 centimeter inverse, and 785 is for lower wave numbers. And over here the green light is the worst performing light source for seeing the Raman spectra. So based on the wavelengths that you are shining, the laser that I am going to shine is going to vary the Raman spectra that we are going to observe. Now, so you can choose your wavelength based on your applications, right? And for biological application, you use autofluorescence. You try to reduce the autofluorescence by using higher wavelength, that is around infrared light source. Okay. So there are specific peaks, as I have been telling, for each of the components. So for example, guanine has a peak between 563 to 567 centimeter inverse. Okay, the lipid has a peak at 744 centimeter inverse. So similar to that, phospholipid has a peak at 978. Okay, so now if you combine, you have a compound which has 2 to 3 components, then you have multiple peaks, and you can actually back calculate or back engineer what component is there inside the cuvette based on seeing these all peaks. Okay. The next thing is to design the Raman spectrometer. How do you make an instrument out of this Raman spectroscopy instrument? So the first thing that you need to have is the light source. Okay, so you shine the light source, you use a beam splitter. Now what is a beam splitter? Beam splitter is a device which is used to transfer the light, reflect the light 50% and transmit the light 50%. Here you can see this is the beam splitter. I am shining the light which is 100% and 50% it is reflecting, 50% it is transmitting. So when you see this transmission characteristic of the beam splitter, it's 50-50. Okay, transmission is 50%, reflectance is 50%. There are different kinds of beam splitters available in the market. There's a 30-70 beam splitter where you can see 30% is reflected, 70% is transmitted. Okay, the first thing is the beam splitter, and then you need to have, so once the beam splitter is there, you shine the light, it reflects 50%, focus using the optics lens, optical lens, and then focus it to the sample, and then it interacts, and the backscattered light goes again with the 50% that it allows through the beam splitter to this filter. Now this filter will filter out. So when you see the actual signal from any sample, it will be all the 3 signals or 4 signals actually. You have the actual laser light source, you have the Raman scattered light source, you have anti-Stokes, and also the fluorescence, autofluorescence. Okay, so you actually need to remove the original light source and the anti-Stokes scattered light source and only focus on the Stokes shifted Raman scattered light source. So how do you do that? You actually apply a long pass filter. Either you can use a long pass filter, or you use a notch filter to remove, in addition to the long pass filter, to reduce the intensity of the light source, because the laser will have significant light source, okay, light intensity. You have to reduce that intensity with a OD of 5 to 6 to reduce it significantly, so that you actually observe only the Stokes shifted Raman spectra. Okay. So there are different kinds of filters available in the market that you can actually use, but basically for this you need to use a long pass filter. Once you use the long pass filter, then you only have the Stokes shifted Raman scattered light which actually focuses, and then it goes to the spectrometer that we have been discussing in the starting. So we have a mirror over here that goes to a dispersive media such as grating, and then it disperses all the different components of light source in different angles, and then it goes to a detector. Okay, for this in spectrometer it requires only around 1000 linear elements, but if you're doing for Raman spectroscopy, you need to specifically capture this peaks, you need even more sensitive resolution. It could be of around at least 2000 to 3000 elements are required in the detector to accurately detect the peaks, otherwise the peaks will not be getting detected. There are different various configurations the Raman spectroscopes are available. This is the most conventional Raman spectroscopy, that is you actually shine the light in the center and you capture with the same path. You can also shine the light and detect it after it interacts through this tissue deep inside, and then you detect it, or you shine the light in the center and you actually in annular configuration you try to detect it. The opposite you can do, you shine the light in an annular region surrounding the tissue, and in the center the back scattered light which actually propagates inside and then it comes out. Okay, so here you can see the light source is going to come in and it's going to back scattered. Okay, and then those lights actually you can detect over here. And then you have the defocusing SORS. What is SORS? It's spatially offset Raman spectroscopy. Here you focus not in the center, but you focus in a broad area, and then you try to capture in the same path. And then you have transmission based Raman spectroscopy, which you shine the light, maybe it's more or less in the terms of the slides, you shine the light in the tissue and then you detect it on the other side of the tissue, slide for example. Okay. You can also use fiber based Raman spectroscopy techniques, where you actually use optical fibers and you use a notch filter to focus the Raman spectra out of it, or you use a ball lens. Ball lens are used for focusing the light at a very small point, as you can see over here in the tissue, which you can actually use to pass through and detect the signals from here. So fiber based Raman spectroscopy systems are actually more portable. So because it can actually, whichever area you want to do, you can actually test it out. Okay. So there are many Raman systems available in the market. You can see over here, this is a tabletop system which is available in the market to get the Raman spectra. And then there is one more portable handheld Raman spectroscopy system also available in the market, with which you can actually detect the composition of any particular powder. Okay. So that's it from my side for this session. So just to summarize what we discussed that when you shine the light on the skin, I am shining a red light. So it's not just the red light that you are observing in your eyes, but it is in higher wavelength of light, means little bit 5 to 10 nanometers from the red, you will see additional spectra, additional signature for different components, constituents. I am shining in the skin, that signature would be different as compared to signature that you see on my nails, because that is made of keratin. Okay, we talked about how to make a Raman instrument, how do you remove the red light and actually focus only the Raman spectra. Okay, so we talk about two components, we have Anti-Stokes and Stokes. We try to say that because the intensity of the Anti-Stokes is like very less, we try to focus on Stokes shifted Raman spectra, and that spectra peaks are specific towards specific composition. So phospholipid, collagen, they all have a specific peaks at particular location. Okay, and if you are able to see those peaks, then you can actually say that that particular component is present or not over there. Okay, we talk about the Raman complete spectroscopy. We use the beam splitters and the long pass filter to remove the actual original light source, and then we use a spectrometer with a very high resolution detector, around 3000 detectors in a linear detectors to actually detect the spectra out of it. And with that we can actually have a lot of applications, like trying to understand whether the pearl is original, whether the map is original or not. We can also detect it also on the oral pathology. For example, you try to take Raman spectra from a cancerous tissue, that would be having different as compared to the normal tissue, right. So, there is a lot of research work that is going on those lines as well. Okay. So, that is it from my side on the Raman spectroscopy. We will meet next time to discuss the other applications of in the case of biomedical optics. Thank you.